Hello everyone, my name is Rong, and the name of our paper is called TAMAA, UPPAAL-based Mission Planning for Autonomous Agents. This work is done by me and my supervisors, Edward Enon, Christina Siciliano from Mälardalen University in Sweden. And this picture shows the use case scenario that we are facing. It is an autonomous quarry, contains an autonomous reloader on the left-hand side corner. So it needs to dig stones in the stone pile and go to the primary crusher to crush the stones into fractions. And then it just continues to go to the secondary crusher on the right-hand side, which is the final destination of it. And during this process, it needs to avoid all kinds of obstacles and go to the charging point when the battery level is low. So we can say that in this environment, we have some milestones where the agent needs to go to finish all kinds of tasks, like dig stones, load stones, unload stones, charge itself. And there are some static obstacles that the agent has to avoid in the environment. And all the tasks need to be done within a certain time limit because the industry wants some productivity in this query. So is the path planning algorithm enough to solve the problem? This picture shows the result if you run theta-star algorithm to calculate the path in an environment filled with static obstacles. And it is able to generate the shortest path from the starting point to the destination and avoid all the black dots, which are the static obstacles in the environment. But if we have some complex requirements, like dig stones at the stone pile, then carry and unload them into the primary crusher, always avoid obstacles and keep repeating these tasks until the stone pile is empty or the vehicle needs to charge, and finish all the missions within 10 hours. Something like this is not solvable by using path planning algorithms. So here comes our motivation of the study. We want to propose a new approach to synthesize mission plans that is guaranteed to satisfy complex requirements like functional and timing ones. And we want to synthesize reliable mission plans quickly, easily, and automatically. But when we are facing some multiple agents, how scalable the method is still unknown and crucial. So we want to answer these three questions in this paper. Previously, we have proposed a two-layer framework to model and verify autonomous agents formally. So it contains two layers, the static layer and the dynamic layer. In this paper, we focus on the static layer, which is responsible for generating mission plans in a static environment containing static obstacles and milestones where the tasks are supposed to be carried out. And all the concrete trajectories like the movement and the unforeseen obstacles, moving obstacles are considered in the dynamic layer in the bottom. So when you are wondering about the collision avoidance between the agent and moving obstacles, something like that, it's not in the scope of this paper, and refer you to the paper that we published 2 years ago in the slides below. So in this paper, we use TAMAA as the modeling language and UPPAAL as the tool to build the model. This picture shows the very simple example of TAMAA. It contains locations and edges, so it looks like a finite state machine, but it's also extended with real-valued clocks. Like the equation on the edge x less than 5, it means when the clock variable x is less than 5, this edge is enabled. And we have some channels named press to synchronize the transitions between different TAMAA. And we use timed computation tree logic to formalize the natural language requirements. We use only 4 forms of them in this paper. So by using this logic, we can express something like something is always satisfied in all the states of the system model, or something will be eventually satisfied in the system model. And we can even specify the concrete time when the property is satisfied. And that is why and how we can express this timing requirement. So now we can have the overall challenge. In a given environment containing one or several agents with accurate speed control and deterministic speed range, and some predefined milestones and static obstacles, and a set of requirements. We want to synthesize mission plans for these agents in this environment such that the requirements are satisfied. To solve the problem, we proposed a method called TAMAA, TAMAA-based planner for multiple autonomous agents. It is called TAMAA-based because the model is built by using TAMAA, like it is shown in the center of this graph. We have three types of TA, which is short for TAMAA: the movement TA, task execution TA, and the monitor TA. The movement TA concerns the connecting relations between milestones and the traveling time among them. But we don't need to know the real trajectory how the agent moves because it is only about mission plans. So the information of traveling time is enough, right? And the task execution TA models the execution time, the best execution time, worst case execution time, and the preconditions of tasks like something has to be done before something starts, right? And monitor TA simply observes some signals in the system, like the battery level. When it's lower than a threshold, it just informs the task TA to respond to it, to go to the charging point, anything to schedule the agent to react on it. So now this picture shows the overall process of the method. In the beginning, the user needs to specify their requirements and configure the environment in this MMT gray. It's called MMT because it's short for Mission Management Tool. And all the information is transferred into the module called the TA generation, where all the TA models are generated automatically. And then the models are checked in this model checker against the queries that is formalized from the requirements. After that, the model checker can generate this execution trace of the model, which is then used to generate the final mission plans. So essentially, we have to design this TA generation module. First, we want to abstract the environment. Picture A shows the very simple draft of an environment with a static obstacle in the center and three milestones surrounding it. So picture B shows how we discretize the environment into a Cartesian grid. The size of the cells must be proper to represent different static obstacles, but not too small, so we increase some unnecessary time consumption. And picture C shows the result of running fitness algorithm to calculate the path between milestones. Picture D is based on picture C, which is a weighted directed graph. So it just tells the agent if you start from milestone A and wants to go to milestone B, it will take you 5 time units, and you don't need to go to any other milestones during this trip. Okay. So based on this graph, we give this formal definition of the movement of autonomous agents. You don't need to read all the text in the screen. We only want you to know that the definition is based on TAMAA, a formal model. So we can design this model generation algorithm to generate the model of TA automatically. Similarly, we have the definition of tasks and task execution and the monitors, of course. And then we have the model generation algorithms. And based on the algorithm, we can generate this task execution model, TA model automatically. And the monitor TA, of course. And the movement TA and the task execution TA is synchronized by the channel move. And the task execution TA and the monitor TA is synchronized by the channel down. So altogether, all these TA models are composed into this network of TA models. In the center is the task execution TA, which makes decision. So it is the time to move for the agent, or the time to execute some task, or to respond to some event from the monitors. is on from the task execution TA in the middle. Okay, since now we have the formal model, it is time to formalize the requirements. First requirement is called task coverage. The agent has to cover all the tasks. And we design the CTL query in this red words. So this query means in the state space of the system model, there exists one path that has at least one state that finish all the tasks from task 1 to task j, and the volume of the stone pile equals to 0, which means all the stones are carried to the destination. Okay. The second one is called task matching. So some certain tasks has to be done at some certain milestones. If you assume the task Ti is allowed at milestone Pi, then we have this universal quantifier A square, which means in the system model, all the states has to satisfy the following predict. Okay, so this query simply means if the task execution TA is at location Ti, which means the agent is doing task Ti, the milestone TA, the movement TA has to be at a location Pi, which means the agent is at location Pi. Okay. The third one is task sequencing. The order of task execution must be correct. So if we assume that task Ti must be done before task Ti plus 1 starts, we have designed these two queries to verify this requirement. The start and finish are two Boolean arrays to denote whether a task is started or finished. Okay. So the first one means in the state space of the system model, there exists one state that let the task Ti plus 1 start. Okay. And second one means for all the states of the system model, if the task Ti plus 1 is started, it implies that task Ti is finished. And the fourth one is timing requirement. All the tasks has to be done within n time units. This is what the timing requirements requires. So this query is designed very similar to the previous one, the first one. It also contains all the tasks from 1 to j and the stone piles volume. But it also has a clock called a clock whose value must be less than n time unit. So n is the time limit to finish all the tasks and carry the stones. Last but not least, we have the event reaction requirement. Some special tasks must be triggered by some event, like battery level low event. But we actually don't need to design some specific queries for this requirement, because the fact that these two queries are satisfied just implies that this requirement is satisfied. Why? Because if the agent wants to finish all the stones, the time consumption is much longer than the time consumption of the battery. So during this process, the agent must have been to the charging point to charge itself. Otherwise, it just doesn't have enough energy to finish all the tasks. Okay, so now we come to the implementation of the approach. We just implement the TAMAA into this Java code that we don't need to go to the details. But we want you to know that on the right-hand side, the code is connected to the graphic user interface called MMT. So the user can configure the environment and show and look at the result of mission planning graphically. On the left-hand side, we have the model checker called UPPAAL, and the code is connected to UPPAAL. So everything is done underneath. Users don't need to know the formal models underneath, but it still have the formal model of the condition to guarantee the correctness of the mission plans. These two pictures shows the result or the result if you run TAMAA in this tool. Picture A shows the a reasonable environment. So TAMAA is able to generate this path plan, like these blue lines in this environment with three static obstacles. But in picture B, we have this unreasonable environment. The only corridor between two static obstacles is blocked by these highlight obstacles on it. So TAMAA can also generate a counterexample and show it in the graphic user interface to let the user know that this is where in the environment it is contradictive. And then we run some evaluations to know the applicability of our method. We designed 3 scenarios. The first 2 contains 1 wheel loader, but the third one contains 3 wheel loaders that need to cooperate to finish some complex tasks. I don't have time to show you all the results, but I can tell you all the 3 scenarios are managed, and we can synthesize mission plans for all of them. But when it comes to the evaluation of the scalability, things change a little bit. First, we increase the number of milestones and tasks. So even if we increase the numbers to 100, like it is shown in the last row of the table, the time consumption of verification is only 29 seconds, which is reasonable. But if we increase the number of agents, it's tricky. For the reachability property, if the agents are 5, the tool TAMAA couldn't generate any result and shows out of memory error because it just exhausts all the physical memory assigned to it. And this is because the increased number of agents simply increased the number of interleaving transitions, and this just increased the complexity of the model exponentially. And so that's why we encounter this state space explosion problem, which is very common if one uses model checking technique. So we are trying to solve this problem right now by using some machine learning algorithms that we will show you in our future work, perhaps. Okay, so to conclusion, we solved the mission planning problem for multiple agents, and we propose and implement our method called TAMAA. The method depends on rigorous definitions of concepts and provides model generation algorithms, so users don't need to know the formal definitions under it. The approach provides automatic and user-friendly means of synthesizing mission plans that are guaranteed to hold the requirements. Applicability evaluation shows it works correctly dealing with single or multiple agents in different scenarios. In the future, we want to improve the approach to handle more agents by using these machine learning algorithms. And we want to integrate TAMAA into the two-layer framework that we mentioned before so that it can cope with uncertainties and moving obstacles in the environment. Okay, that's all for my presentation, and any questions are welcomed, so just contact me without any hesitation. Thank you.